From Claude to Gemini to DeepSeek, claims of reasoning large language models are everywhere. With reasoning language models, before responding, the AI pauses to think. It starts with a thought, then gives an answer. The open source floodgates are wide open. There's SFT, DPO, GRPO, and many more. There's new methods, new models, and new acronyms every week. In this video, we'll focus on one method at the heart of the recent reasoning AI wave: Group Relative Policy Optimization, abbreviated as GRPO. We'll discuss what GRPO is, how post-training makes models reason at inference time, some experiments we ran, and diagrams to explain what's going on under the hood. In 2025, the best teams aren't just prompting, they're designing intelligent systems. The differentiation comes through custom data, context engineering, and how methods like GRPO can shape customized model behavior at inference time. If data is oil and compute is gas, training methods like GRPO optimize the engine mechanics. GRPO is like shifting an F1 car into high gear. So, you want to build models that think? Let's wade into building an LLM reasoning stack. Before models can reason, they need to speak. Pre-training teaches them how. LLMs start with random weights and learn by predicting the next token in an internet-sized pile of text data. But raw language isn't enough. In practice, models are further post-trained to align with goals like helpfulness, safety, or style. These post-training layers turn base models into the models and applications that we interact with, like ChatGPT, Llama Instruct, or DeepSeek R1. Take DeepSeek R1. To reach its final form, the base model was repeatedly post-trained, first with supervised fine-tuning, then with the novel GRPO method. The GRPO model is even used to generate SFT datasets for future fine-tuning rounds. GRPO builds on an earlier method called proximal policy optimization, or PPO. Both use reward signals to bias the model toward better responses. GRPO makes it easier to specify the reward function and empirically performs well, both performance-wise and on computational efficiency, a major reason why it's catching on. Like PPO, GRPO casts LLM post-training as a reinforcement learning problem. Starting from a base model, the goal is to update the model's weights so that the model learns to generate preamble text at inference time, otherwise known as a chain of thought, before giving an answer. To do this, GRPO generates a group of samples per batch, computes rewards for each, and then derives a backpropagation signal by comparing their relative differences through a value called the advantage. For each generated response, the advantage directly changes the loss function, and thus how much and in what direction the model is learning. We can use GRPO routines in any Python reinforcement learning library. Two standouts include Hugging Face's TRL library and Meta's TorchTune library. Both scale naturally to multiple GPUs, multiple nodes, and support group-based reward logic out of the box. But flexible software is only half the story. To run post-training at scale, you need GPU infrastructure and a scalable compute provider. Here, for example, we see the same TorchTune script from before running inside of a Metaflow workflow, which connects us to GPUs in Nebius Cloud. We started with an experiment on the grade school math data, a standard dataset produced a few years ago by OpenAI. We trained the model to reason in a format that it was never explicitly taught, using GRPO and a custom reward function. In this training run, using the Llama 3.2 instruct model across 8 H100 GPU cards, we see the model quickly learns to solve these basic math problems correctly. We observe clear improvement in the task at hand, and something resembling reasoning from scratch to solve simple math problems. For a few dollars in compute spend, the GRPO method teaches a 3 billion parameter model to generate the kinds of text patterns powering DeepSeek. But what happens when the reward pushes the model to do something unnatural, like keeping the same dataset and prompt, the grade school math dataset, but rewarding the model for generating strange answers like AAA characters in a row? The model tries, it hacks toward the target, but it plateaus. Why? The reward is misaligned with its training distribution. like having a calculus teacher that grades your math test on the basis of arbitrary words being in your derivation. This toy example shows a limit of GRPO. If reward functions don't align with language priors, prompts, and data, you won't get useful outputs. To test GRPO's versatility, our final experiment was run on a dataset built from Project Gutenberg, where we sampled passages from novels in different historical eras, each sample coming from a different era, and the task being to predict the publication date. After learning how to format responses, the model learns to infer extra preamble, explaining its choice of era based on the input. The GRPO method adapts our model, but it's fragile. The reward can quickly guide the model towards explaining its reasoning behind the classification and regression tasks. But is it reward hacking? How do the effects vary across model sizes? And could a bag of words do it? At this point, a normal data science search ensues. So what did we learn? GRPO makes reinforcement learning more practical for language models. With a few lines of code and a clever reward function, you can shape how models reason. But it isn't magic. The reward must align with the task. The prompt, data, and reward function need to work in unison to define the desired behavior of an LLM at inference time. And you'll still need to debug a lot. If you're eager to get started at your organization today, Outer Bounds gives you the tools to run GRPO at scale. Orchestration, monitoring, and compute infrastructure out of the box. Start building the next generation of intelligent systems today.